Okay, I guess we're ready to continue. So here's the equation. And if you look at it, first part of the equation, okay, so H naught minus H, that's the drawdown. That is this quantity right here. Remember, this equation is telling us how far is the water table going to dip down due to somebody's pumping at some distance away from their well. Okay, so we have this well. Right near the well, right at the well, it draws down the most. And as you move away, as R in this case gets bigger, the drawdown is less and less and less. And, you know, at some point you're going to be so far away from this well that there isn't going to be any drawdown. But this equation is going to tell us what the drawdown is. So it has to do with the Q, the pumping. You can see in this equation, the more you pump out, the greater your drawdown is going to be. That should make sense, right? So right here, there's your Q. As Q goes up, your drawdown is going to go up. Okay? But then you guys probably noticed this thing right away, right? Scared the crap out of you? Well, this is something called the Tice equation. And as it turns out, this part of the equation is very, very, very difficult to solve. Even for PhD mathematicians. It's one of these mathematical expressions that doesn't have a good solution. So what happened was, this is a problem that had been worked on for quite a while. A mathematician named Wenzel, back in 1942, came up with a numerical approximation for it. In other words, he couldn't solve it, but he came up with an equation that came pretty close. For practical purposes, it works. So he came up with a numerical approximation. And the equation then becomes this. First part's exactly the same. And the second part of the equation that is so difficult to solve, he came up with sort of a sub-equation for solving that part of it. WU, where U equals R squared S over 4T, big T, little t. Go ahead and write this down. We'll go through this in a minute. I'm going to give you what all this stuff means here in a second. I just want you to be able to catch up on the notes before I jump over. Okay, so let me jump ahead and put the equation back up. Okay, so that's what we had on the previous page. So that nasty equation becomes this, which is not such a nasty equation. Now it's just algebra. The first part, Q over 4 pi t. I'll define what these variables need in a minute. And then the second part, the W sub mu, where mu equals r squared s over 4tt. What you do for this is you solve for this quantity right here, okay? And that's pretty easy to do. I'll give you the values for this in a second. That gives you the little u, okay? And then remember that Wenzel guy? He came up with an approximation using this u. You look in a table and find out what W of u is. And I'm going to give you this table, okay? He came up with this approximation. It's a rather famous approximation. And you look up, based on u, what W sub u is, and you just plug it in there and you calculate it through. So let me just give you these variables first of all. Q is the pumping rate. In cubic meters, rewrite that, cubic meters per second. H naught was the total head before pumping. We measure that in meters. H is total head after pumping. Measure that in meters. T is a new value we put up. Not sure why they do this. It's KB. They could just put KB in there, but T is a value called transmissivity, and it's fairly common in hydrology textbooks, so I figure it's worth at least mentioning it to you here. But it's basically the hydraulic conductivity multiplied by the aquifer thickness. Aquifer thickness we measure in meters. Hydraulic conductivity is meters per unit time, meters per second, or meters per day. Little t is the time. The longer you pump, the more drawdown you get. R is the radius or the distance that you are away from the well. And S is the storativity. Value I talked about a little earlier, it's dimensionless. Okay, so that's what all the variables are. All right, now I'm going to give you an example and we're going to use it. You're going to find out, you know what, this really isn't too bad. Probably looks terrible right now, all these different variables and some crazy looking math early, but what I need to give you, though, is I need to give you this little chart with the W sub U values. So for those of you in class, I'm going to hand it out. For those people at home, or if you want it later, I'm also going to put it on the website. See if I can find it here. Here it is. Okay, so the chart I just handed out, or that you pulled off the website, It has basically two columns. It has U and WU. So what you do is you calculate U. If you look at the notes here, U is R squared S over 4TT. You calculate that, okay? So let's say you calculate that and you get 4 times 10 to the minus fifth. What you do is you find 4 times 10 to the minus fifth under the U column here. And if you look, you'll see that it's actually in the third column. What you do then is you take the value for WU, which in this case is right next to it, 9.55, and you stick it in your pumping equation. So basically you multiply Q over 4 pi T and then multiply by 9.55. So all that nasty math becomes a single number. It's kind of beautiful. And if you're, if you don't appreciate really difficult mathematics, this is great. Boil down something, a really nasty integral to a single value. It's wonderful. So this chart is your best friend. Okay, so let's do a problem finally. Okay, after an hour and 10 minutes of going through this stuff, let's do a real problem. Okay, let's say that we have a well located in an aquifer. The aquifer is confined on top and the bottom. With no recharge. This aquifer has a hydraulic conductivity. This is something that groundwater geologists would get from a slug test or from other modeling that they might do in the aquifer. But let's say they have a hydraulic conductivity of 14.9 meters per day. Okay? So that's the value for that aquifer. If you go to a different aquifer, somewhere else, a limestone, something different than what you have here, you might have a slightly different value. Storativity of, why did that change color? That's interesting. 0.0051. Remember, storativity is dimensionless. An aquifer thickness of 20.1 meters. And a pumping rate, Q, of 2,725 cubic meters per day. What is the drawdown? How much does the water table lower if you are 7 meters away one day later? Okay, so you have this aquifer. It's got a confining layer on the top. It's got a confining layer on the bottom. You put a well in it, and some guy sucks out 2,725 cubic meters in a day. How's that going to lower the water table? How much will it lower the water table 7 meters away, one day later? So go ahead and sort of plug and chug this and see what you come up with. And I will do it here as well. Okay, I haven't worked through it yet for you, but when you get an answer, throw your hand up. What'd you get? 2.16. Okay. Anybody else get an answer yet? Or you just run into a dead end and just throw your hand up too. I want to give you enough time to work through it, but if you just dead ended, I don't want you to sit there all night. Now make sure once you calculate U that you look up the W sub U and use that number in your equation, or you'll get a really tiny number. Yeah, Keaton.
5.66.
Bingo. And that makes sense. It can't be less than nothing, and it can't be more than 20.1. It's got to be between not dropping at all, which is 0, and the bottom of the aquifer, which is only 20.1 meters thick. Okay, let's go through it. If you're getting close, you can keep working on it. So I've set it up to some degree, okay? So here's the pumping equation right up here on top. All right? And I've given you some of the values that you need over here. So let's plug in what we have already. So this first part of the equation is pretty straightforward. You've got your pumping rate of 2,725 cubic meters per day divided by 4 pi T, and T is the hydraulic conductivity, which I gave you, 14.9 meters per day, times the aquifer thickness, 20.1 meters. Multiply those together and you get a T of 299 meters squared per day that you can just pump back into your equation there. And then the second part of the equation is this W sub U thing right there, okay? So to find W sub U, you first have to find U. U is R squared S over 4TT. R is the distance from the well, 7 meters. S is the storativity. I gave you that value, 0.0051. Just plug those in. Over 4 TT. 4 times T is 299. Your little t is days. It was 1 day. Now here's something really important, especially for the next problem I'm going to give you. The only thing you really have to look out for in terms of units is right here. Okay? I'm going to do this in green. Are these two units right here? The big T and the little t. The time unit has to be the same. Okay? In this case, your big T is in meters squared per day, and your little t is in days. What's going to happen is these units are going to cross out. You're left with meters squared on the bottom. If you look, you've got 7 meters squared. So you have meters squared on top. All the units cancel out. That's exactly what you want. You want all these units in this U to cancel out. So make sure that your big T and little t have the same time. And the next one, they're going to have different time, which means you're going to have to do a conversion to get them to the same time. I'm just going to warn you that ahead of time right now. Well, if you multiply all this out, your little u should come out to 0.00021, which is the same thing as 2.1 times 10 to the minus 4. Okay? That's your u. Then what you do is you get out your little chart and you find 2 times 10 to the minus 4. If you look in the third column, you see it starts, the top is minus 5, then it's minus 4, 1 times 10 to the minus 4. There's 2 times 10 to the minus 4. The W sub u value that goes with it is 7.94. Okay? So what you do, let me get rid of some of this nonsense here. You take that 7.94 and you stick it right there, and you multiply everything out, and you should be left with 2725 meters cubed per day over 4 pi 299 meters squared per day times 7.94. And if you multiply that out, you end up with 5.7. Take a look at your units. You have meters squared per day on top, meters cubed per day on top, meters squared per day underneath. That leaves you with meters. Okay? That's how you use the equation. The hardest part, calculate U, then find W sub U, and stick that number back into the original equation. And then you just multiply stuff out. All right, I'm going to give you one more problem to do. Any questions on this? Any part that you got hung up with that you don't understand how to go through it? All right, let me give you another problem. I actually love this next problem, okay? This is like a super practical problem. So I hope you enjoy this. So we've got a guy named Marty. Marty's house is located 1 kilometer from a golf course. That recently drilled into the same confined aquifer that Marty uses at his home. So Marty's been using this confined aquifer. Now this golf course comes along, drills into the same aquifer. I think you can see where this is probably going. Okay, this aquifer is 30 meters thick. "100 feet. Decently thick aquifer. And he knows it's that deep because of drilling records in the area. Well, Marty just uses water for home. And when he put in his well, he didn't want to make it unnecessarily deep. So Marty's well only penetrates the upper 15 meters of the aquifer. But the golf course, they knew they were going to suck a lot of water out. So they put in a golf course well that penetrates the entire thickness. The entire 30 meters. So Marty does a little poking around, and he discovers that the golf course has been pumping a ridiculous 20,000 cubic meters per day for the last 3 months. And guess what? Marty's well is now dry. My question to you is, the golf course fully, partially, or not responsible for Marty's dry well? The aquifer has a hydraulic conductivity of 1.8 times 10 to the fourth, 10 to the minus fourth meters per second, and a storativity of 0.0065. Pay attention to the units. Make sure your units cancel out. Try to figure out, did the golf course make the water table under Marty's house drop by more than 15 meters? If it did, then they're probably the reason his well is dry. But if it didn't, then there's something else going on. And I will do this as well. I'll just let you know that if you work through this and got the answer right the first time, you're in rare company. It almost never happens. There's so many little places to make small mistakes on this one. So if you didn't get it right or missed a little thing here or there, do not worry about it. I'm going to give you some additional chances next week. Next week I think we're just going to do some practice problems. And just make this stuff work so that you get more comfortable with it. I don't think I'm going to add any more new stuff. All right, you want to go through it or you need a few minutes? You want a minute or two? Yeah, take another minute or two. Yeah. The radius. Okay, so he is a kilometer from the golf course. Okay? So that's the radius. That's the distance that you're interested in. And just remember that everything else we have here is in meters and days. So just take that kilometer and make it into meters. So you'll see in my problem here that let's see, where is it? Right here, I'm going to do this in red. R squared is going to be 1,000 meters squared. So that's one easy place to make a mistake, okay? The other easy place to make a mistake is way down in the lower right, where you have 4t little t. Remember, the little t is the time that you've been pumping. And since everything else is in per days or days, might as well change that to days right away. And we said 3 months, so just assume 30 days per month and make it 90 days. And I was kind of a jerk and I gave you your K value in meters per second when everything else is in days. So changing that to meters per day requires a conversion, which is what we have going on right there. So there's 3 easy places to make a mistake just with conversions. So actually, this is about as hard a problem as I will give you. I probably won't give you a problem this hard on the final. This should be harder than anything you do on the final. Or at least as hard. It won't be harder. Okay, let's go through it. We'll go through it pretty quick here. So all of these equations, all of the equations that we're going to use here have really two parts, okay? First part is you got to find this u, all right? So that you can look in your chart and find the w sub u. So let's find out u. So I did u down here in the lower right, but let me just get rid of it and we'll go through it here. All right, let me erase all this. Okay, so u equals r squared s over 4t little t. R squared, what is R? R is the distance that you are from the well. The only challenge to this is just putting it in the right unit. I said he was a kilometer away. Everything else is in meters. It's easier if you just, right from the get-go, just stick this as 1,000 meters. And then you're going to square that value. I gave you S. S is 0.0065. It's dimensionless. Over 4 big T. Big T is the same as KB. I gave you K, 1.8 times 10 to the minus 4th meters per second, but there's one of those units that you got to convert to days because everything else is in days. Alternatively, you could do everything in seconds too and do it that way. It doesn't really matter because they're all going to cancel out at the end. But we can take 1.8 times 10 to the minus 4 meters per second and change it into days. There's 3,600 seconds in a day, or you can think 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and do the math. Anyway, you end up with a t value of 465 meters squared per day. So let's put that in right here. And then times the time. And I said we've been pumping for 3 months. Since everything's in days, put it in days. 3 months is 90 days, okay? If you multiply that all out, I ended up with a U of 0.038. Or 3.8 times 10 to the minus 2. Now, if you look at your chart, there's no 3.8 times 10 to the minus 2. The closest thing you have is 4 times 10 to the minus 2. So for our purposes, we will go with 4 times 10 to the minus 2. And if that's the case, your W sub U turns out to be 2.68. So U is 2.68. You multiply 2.68 times the rest of this equation. Q over 4 pi tt, which I've done down here on the bottom. And if you multiply all that out, all the units should cancel out, leaving you with meters, and you should end up with 9.1 meters. So what this equation is telling you is that at a kilometer away from the golf course, the golf course's pumping should have lowered the water table by 9 meters. Is that enough for Marty's well to go dry? How far did Marty drill down? 15 meters. Well, the golf course is responsible for 9 meters of drop. If that was all that was going on, would Marty's well be dry? No, you'd still have some water. You'd still have 6 meters of water in there. So, golf course is partially responsible. Somebody else is sucking water. So that's a pretty practical question that you can answer with this equation. And this is what happens in water court all the time. People's wells go dry, they claim somebody else did it. Some hydrologist like me will come along and do this calculation and say, hey, no, they're not totally responsible. They're only partially responsible here. And then what the other side would do if they were smart is they would get their own hydrologist and say, Anderson's an idiot, he used the wrong equation. Because it really isn't a confined aquifer. It's this kind of aquifer, and you're supposed to use this equation. So that's why you have to make sure that your equations fit the conditions that are there. So this is stuff that really gets used out in the real world for practical purposes, for legal purposes, for whatever. So I don't want you to do any more work on this week. You've got your homework to do. Work on that. Next week I'll give you a few of these to practice on, and we'll just spend the class period practicing problems so that you're ready for the final. Sound good? All right. You guys go have a good night, and I will